Okay, subgroups in a group. So we have a couple examples now of this idea of subgroups. Let E equals 1, 1, 2, 3, 1, 3, 2, 1, 3. Show that E is not a subgroup in S3. Multiplication table for E. So we have 1, 1, 2, 1, 3. 1, 3, 2, 1, 3. It's 1, 1, 2, 3, 1, 3, 2, 1, 3. And we do this until we get a contradiction, which does not take long. So multiplying by 1 obviously gives you the row of the same thing by identity. Yeah. So then 1, 2, 3 times 1 will be 1, 2, 3, of course. Then 1, 2, 3 times 1, 3, 2. You could refer to the table at the back of an abstract algebra book usually, but how about we do this by hand real quick just to do some more cyclic notation, because these are all cycles in cyclic notation, these ones. The group S3 has six technically terms, 6 different permutation terms. There's just 4 of them. That's why it's a subgroup though as well, real quick. Because if it is a subgroup, it would only contain so many of the permutations. In this case, of the permutation group of 6, it only have 4. But it's not going to work out as seen here in pink. But it even says not why it's not. You're supposed to show. But besides the point, so basically you get 1 goes to 2, 2 goes to 3. So 1 goes to 3, 2 goes to 3, 3 goes to 1, 2 goes to 1, 3 goes to 1, 1 goes to 2. Goes 2. Then you have to rearrange it so you start with 1, of course, always, and you make it so that it ends here at 1, basically 1, and you keep on being 1, 3, 3, 2, and then 2, 1. So 1, 3. That's why it's called a cycle after all. In the previous section we had diagrams, and now with cycles as part of what. So 1, 3, 2. But the equivalency, this and that are the same. Same as this and that. So 1, 2, 3 times 1, 3, 2. Same deal as before. Eventually you get, this time we get the identity though, 1. 1 to 1, 2 to 2, 3 to 3. Then 1, 2, 3 times 1, 3, we end up with a palm here when we do it. Was actually when we get the result, normal process, we get 1 goes to 2, 2 goes to 1, 3 goes to 3, so it's just 1, 2. 3 goes into itself, and so it's not in that notation then. Just 1, 2, but you see a group has to have closure. Closure means that in the multiplication table you'd only observe the values of the multiplication table itself. Like these 4 different permutations that are only 4 permutations in this case that you would observe as a product of permutations, pretty much. So 12 is not included in the set E. Closure of E is not satisfied, so E is not in the group E, of course. That's the same thing. It's a set of the group E, so it's not included in E. Closure of E is not satisfied, so E is not a subgroup of S3. 18. For each of the following conditions, we have 2 we're going to look at. Explain why the set of all permutations theta on xn equals 1, 2, n that satisfy the given conditions. Gives addition is or is not a subgroup in Sn. So yeah, basically you have to figure out if that satisfies the given conditions, and theta is not a subgroup in is or is not a subgroup in Sn. So yeah, Sn is of course permutation groups. So all permutations possible in this conditions, So first one is just theta 1 equals 1, and you can rewrite this in a more formal way as h equals, and you're going to check for if stuff is included in h. H equals theta is included in Sn. Theta is in Sn such that theta 1 equals 1. So theta 1 means the first. See, the first column, basically the first column will be equal to 1, and whatever you your input will give you an output of 1. What am I looking at? So you check closure first, because we need to have closure and we have to have an inverse. We have to be able to show the inverse property as well. Basically in this case for a subgroup and a group. So let's say the 1 is in H, say the 2 is in H. And for this problem, just say the 1 equals 1 goes to 1, 2 goes to A2, 3 goes to A3, dot 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 n, dot an. Keep on going. 1 goes to 1, 2 goes to B2, 3 goes to B3, and so on. That's theta 2. So they both 1 goes to 1 basically, if these are in H. And then we have to see if theta 1, the product of theta 1 and theta 2 is in H first. And I'll show closure. So 1 goes to 1, 2 goes to A2, 3 goes to A3, multiply by 1, so on. And obviously 1 goes to 1, 1 goes to 1. You'll get 1 goes to 1 in the product, 2 goes to C3, 3 goes to C3, whatever they will, C2, C3, then eventually n goes to Cn, and that's included in H, obviously. Due to theta 1 times theta 2 is in, theta 2 for the 1 column equals 1, a notation, which implies that theta 1 times theta 2 is in H, so closure is present. Now we have to check if theta 1 times theta 2 inverse is in H. If it is, this will be enough to satisfy our conditions. You show that this is a subgroup. So theta 2 is just, you reverse it, so it's 1 b2 b3 dot dot bn, and the second row is 1 2 3 dot dot n from this. Just flip it. So theta 1 times theta 2 inverses, you still get 1 goes to 1 and 1 goes to 1, basically 1 to 1. So same thing basically, regardless, because you don't know any values beyond 1 goes to 1 basically. But it's still included in H because theta 1 times theta 2 inverse, the inverse of theta 2 in the 1 column basically will be equal to 1. So H subgroup of Sm. Conditions. 18C. Theta 1 is in the set 1, 2. Here let n greater than 2. So in this case we have a little bit more of a little bit harder condition. H equals theta is in Sn such that theta 1 is in the set 1, 2. Check closure. And it looks like closure is gonna fail, we'll see. First we have to set this up like normal. So theta 1 is in H, theta 2 is in H. Want that happen? So theta 1 has 2 values and theta 2 has 2 possibilities. 2 permutations. So 1 goes to 1, or 1 goes to 2 basically is the main difference. So then 1 goes to 1 and 1 goes to 2 for theta 2. And theta 1 times theta 2, we have to check 4 of these. We have to check the multiplication of that, these, that, and that. We have to check them of all the combinations. So there's 4 possible combinations, and there's 2 of them. You multiply each of these individually. So if all 4 of them work for closures and all 4 of them work for the inverse property as seen in the last one, we only do 1 of each. If they all work, then yes, this is a subgroup. So theta 1 times theta 2. The first one is 1. We do the most simple one, and it's obvious because it's going to be 1 goes to 1, 2 goes to C2, 3 goes to C3, and eventually n goes to Cn, which include an H because theta 1 times theta 2 equals 1 for that first column. So theta 1 times theta 2 is an H. But the second one will fail. We have 1 goes to 2, 2 goes to B2. So 1 goes to B2, then 2 goes to A3. So 2 goes to B to C2, 3 goes to C3, and then eventually n goes to Cn. It's not including H because 1 goes to B2. So it's equal to B2 implies that theta 1 times theta 2 is not an H, not include H, because let's say B2 can equal anything. It can equal anything besides 1, pretty much, as long as this works. If we're going to assume this operation is working properly. If it doesn't equal 1, then it could equal 2, which would be good, because if this equals 1 or 2, it works. Is it doesn't have to. So B2 equals 3 can occur, which makes theta 1 times theta 2 equals 3, which implies that theta 1 times theta 2 is not included in H. Not H. Is that H? Is that H? H is not a subgroup in Sn then, because if closure fails, this means closure has not been satisfied. So there's no closure, so therefore you can't even worry about the inverse property, is this group fails already. So find the centralizers of each of the following elements in S3. So now that's one last thing is centralizers that are introduced in this section. And these are just a couple problems that are most important to people doing this. You know, this is more supplementary at the end of the day. So this would be what a lesson would probably be, but so A1, just one. So this is going to be the identity. So it has to be theta is in S3 such that 1 times theta, that identity times theta equals theta times identity, and that's always going to be the case. So in S3, all 6 permutations satisfy. You know, that's what the centralizer will be, all 6 of these. And 1, 2, it's limited to only 2 permutations of the 6. You know, it has to be 1, 2 times theta equals theta times 1, 2. And as you can see, this fails for 4 conditions. And I used the multiplication table this time to make it simpler. And it's convenient. And I've gone over the cycle notation multiple times. So you can try it if you want to, but these are results are good. So 1 and 1, 2 are the 2 cycles. Yeah. That's all you have to do here. So those are for first parts, and final part, you know, is see, we have 1, 2, 3, so the centralizer 1, 2, 3 is 1, 1, 2, 3, 1, 2, 2, because that's where 1, 2, 3 times theta equals theta times 1, 2, 3, as seen here. Because obviously when you do 1, 2, 3 times 1, 2, 3, 1, 3, 2, it equals identity, so 1, 3, 2 times 1, 2, 3 also equals that. Recheck it. 1, 2, 3 times 1, 2, 3, well that's the obvious one. If you multiply by itself, it'll give you the same thing both ways, pretty much. So cycles work. And identity, of course. Identity in itself are like, I think, obvious ones. Just the most obvious ones you'll get. And that's basically it, the centralizers and everything about that section. These couple examples only. The most prudent, the most important examples. I understand subgroups. But that'll be all.